I will explain you lemma 23.3 in this video. Here you can see the statement of this lemma. The union of a collection of connected subspace of capital X that has a limit point in common is connected. So what they are given in the statement is they are saying there is a topological space capital X. Okay, within that topological space you are having collection of connected subspace. Okay, that is you are having union of collection of connected space, and they are saying that this union of collection of connected subspace has a limit point in common. Also it is having limit point. Then what they are asking us to prove is the union of collection of connected subspace of capital X is connected. That is what we have to prove. So first you have to take a collection of connected subspace of X, right? So that is what we are going to do. Let this is the collection, okay, put like this, collection A alpha be the connected subspace of capital X. So you are taking a connected subspace now, collection of connected subspace. That is why you are writing like this. This is the collection of connected subspace. You are taking like this, okay. Let A alpha, collection A alpha be the connected subspace of capital X. Now, then you are taking union of collection of connected subspace of capital X, okay. So that is what you are taking. Let you are writing with union. Union A alpha be the union of a collection of connected subspace of capital X. Now you are giving a value to this union A alpha, that is y. Let y equal to this. You are taking like that. That is at the end of the proof. That is in the statement they are asking us to prove union of collection of connected subspace of X is connected, right? So you are taking this is union A alpha. This is connected. This is connected. That is what we are going to prove. So you are saying that capital Y equal to this. So at the end you will say this Y is connected. Is that clear? Because this equal to this, no, this equal to this. So you can say Y is connected at the end of the proof. So let's see. Also you are taking a limit point within this union A alpha because in the statement they are given you. So you are taking a limit point. The limit point is P here, okay. Let P be the limit point of union A alpha. To prove Y is connected. That is what in the question they are asking us to prove. So you are writing that. Now you are going to prove this in by bringing contradiction at the end of the proof, okay. That the proof is in that format. So what you are doing is you are writing suppose Y is not connected. You are taking like this. If Y is not connected means what will happen? There exists a separation of Y. There will be a separation, right? So that is what you are writing. Suppose Y is not connected, then there exists a separation of capital Y. Then you are writing the definition of separation of capital Y in these two lines, okay. Then Y equal to this, Y is equal to two sets, okay. Two open sets these are. Union of two open sets. You are writing this by what? By the definition of separation of Y, okay. Here these two lines are coming from the definition of separation of Y. So let us read it. This Y is equal to C union D is the separation of Y, where this here you have this C, no, this C not equal, C should not be empty and D is also should not be empty. When you find the intersection of this C and D, that should be empty. Intersection values should be empty. Why? Because you are writing the definition of separation of Y. In separation, if two sets are separated means there should not be any common values between that two sets, right? So when you find the intersection of that two sets, you should get empty. If the sets are separated, you have to get the intersection value empty. Am I right? So that is what you are writing. C intersection D is equal to empty. And here you have C and D, right? The C and D are open in where? Y. Is that clear? Now you are saying that you have wrote that P is a limit point of union A alpha, right? So you have, now you have Y is equal to C union D. What is mean by this? You are having already, you are having P belongs to union A alpha means Y, right? So that is what you are writing. You are having now P belongs to Y. It means what? P belongs to Y. It means what? Either P belongs to C or D. That is what the meaning, right? Y equal to, I hope you know this. C union D, it means what? P lies either in C or D. That is what the meaning. If it is intersection means what you say? P should lie in C and D. I hope you can understand the difference. So, okay, here you have P belongs to Y, so that you can write what? P belongs to D or P belongs to C. P might be lie in C or it may lie in D. Okay? It is not necessary to have this P in both the open sets in Y. Is that clear? Okay. So now after writing this, what you are doing is let P belongs to C. You are taking like this. You are considering this case. Let P belongs to C. You are taking like that. Also you are saying in our first line you have wrote that, what you have wrote in the first line? A alpha is a connected subspace of X, right? So that is what you are rewriting here. P belongs to C. You take like that. Also you are writing, since A alpha is connected subspace of capital X by a lemma. You have a lemma. I will show you the lemma. You can see that. Previous lemma, okay, this is previous lemma. If Y is a connected subspace of X means here you have A alpha is a connected subspace, okay. The value is different, but the concept, the matter they are talking about is same, okay. So here Y is a connected subspace of X means then what you get? This Y lies, this Y, okay, this Y lies entirely within that open sets C or D. That is what the statement, okay. So here in our proof we are going to use this statement now. Here you have A alpha as a connected subspace of capital X. Also here you are having open set C and D. So by that lemma you are writing this A alpha must lie entirely within either C or D. Okay. Now since A alpha contain a point P of C, here A alpha, what you have here? A alpha contain a point P of C. Okay, A alpha must lie entirely within C or D, right? So if A alpha is within C means what you can write? A alpha contain a point P of C. You can write this. Consider A alpha is within C. If A alpha is within C means A alpha contain a point. Why? In C you are having a point P. Now A alpha is also within this C. Right? So from these two sentences, these two things you are writing this sentence. A alpha contain a point P of C. That is P of C means what? P belongs to C, right? You are having C. A alpha is within this. This is C, okay? A alpha lies within this C. Now already you are having a point P within this C. Right? So that is what from this you are writing A alpha contain a point P of C. If that's so, then A alpha cannot lie in D because A alpha in C, right? So how can A alpha, then how could A alpha can lie in D? That's not possible, right? So that is what you are writing. A alpha contain a point P of C. A alpha cannot lie in D. Hence, you can say A alpha contained in C for every alpha. For every alpha, A alpha present inside C. That is what the meaning. So you can write for every alpha, no? So that is why union A alpha also contained in C. Then you know that union A alpha, the value of union A alpha is Y, so contained in C. Now you are writing D, if Y contained in C means D equal to empty, because now you have two open sets. Now you are saying Y is, this is C, this is D, Y lies within this C. It means here you have no elements for D, right? So that is why if Y contained in C means you will get D equal to empty. So which is contradiction, because here you have put D not equal to empty. Right? Open sets should not be empty, but you are getting D equal to empty. So which is contradiction to D not equal to empty. So this, our assumption Y is not connected is wrong. Therefore Y is connected. Hence the proof.